Oh, thank you. Okay, by a show of hands, and by that I mean click a button, how many of you have used or have heard of deep learning? Mainly have used, are familiar with it. Let's see, 1, 2. Okay, so perfect. 3. Okay, great. So that's great, because then this means that it will be a good use of all of our time. Now, this will be a very short, and as all the things that we have done in this summer school, just we hope to give you just pointers, mostly to different ideas of these techniques. These are very I mean, you can get very deep into this technique, and people apply these days to all kinds of stuff. But the main I think idea of deep learning is that the idea behind it is not that new. So neural networks were introduced decades ago, I think 70, 60 years ago. But at the time, the amount of complexity that the neural networks had was not big. Then they realized, okay, they needed to add a little bit more complexity to capture more complicated trends in the data. But then basically the neural networks at the time, I'm talking about the 80s, they had so much complexity that they overfitted the data. So it was very hard to show and demonstrate that they were powerful, because in order to solve the overfitting problem, you need to get a lot of data and a lot of computational power. Now, that changed 10 years ago or more with the advent of big data, with the advent of GPUs that allows you to run these models on lots of data so you can exploit the complexity that they have. And these days, most of the things that you see that you use on your phone, or say for image recognition, for speech recognition, for music detection, for all kinds of stuff, they're based on deep learning. And I believe that in Science of Science, we have an opportunity, because we have, you have seen throughout the lecture on OpenAlex, that we have hundreds of millions of documents and citations that we could, in principle, use for training deep neural network for Science of Science. And if you look at the work that, for example, Semantic Scholar has been doing, they are basically applying in a lot of their products or services deep learning. So go deep learning. Okay, so the way that we will do this, I will just kind of motivate where neural networks come from. They actually were based at the beginning on trying to replicate how actual neurons work in our brain. And then I will go through one of the models that is, it's called a perceptron, and then introduce the concept of layers and training of those neural networks of multi-layer perceptron, and that's kind of generalizes to other kinds of neural networks as well. And then we'll do a little activity just so that you can see why these objects, neural networks, are so powerful. I will introduce it by way of looking at a classic problem in machine learning, and this is image recognition. So if you ask a computer to tell you what object is in each of these images, to you is very easy, right? So this is an animal, like a crocodile or something like that. This is a camera, although from like 20 years ago, this is a chair, and this is a plane, right? So for us, it's very, very easy. But because we have a very advanced visual system. But however, for a computer, the only thing that the computer sees is pixels, right? It just sees, in this case, there were 300 by 200, so 300 width, 200 height, and 3 dimensions, so red, green, and blue. And that's what the computer sees. So it sees 180,000 raw features. Okay, so So we are basically asking the computer to map those 180,000 features into a couple of categories that we can train it to. So if we use something like regression, where the features are really, or the location of the features doesn't, there is no basic interaction between the features in the simple case of linear regression, then it's really hard to make sense of an image with that technique. And the reason is that images have very complex spatial features, local and global features as well. So to describe, let's say, a crocodile, the mouth, I know that it has a more specific name than mouth, but to describe that, you need to describe a set of pixels and the arrangement of those pixels with respect to each other. So it's not just a matter of seeing one pixel and the color of that pixel. You have to look at interactions between them. So how do neural networks do this? Well, we'll try to explain that. So as I was saying, when you ask a computer to classify an image or to detect something, the only thing that it's looking at is just numbers. So if we use something like logistic regression, although this looks like a very complicated equation, this here is how it makes a decision. It just adds the pixels and then the weights of each of those pixels to make a prediction. And because it's just an addition, it doesn't matter it just permits, so you can just if you scramble pixels, it will completely undo what the classifier is trying to do. So it's linear relationships, and it's hard to capture these more complex spatial features. So, so I'm going to skip this a little bit, but basically the inspiration comes from, I think the easiest way of seeing the inspiration of more neural networks is to look at the visual system. So you receive the light through your eyes, and that light is transformed into electrical signal that travel all the way to the back of your brain. And then there is some computation, these neurons, some sort of activity that happens here that is directly affected by the light outside of your head. And that gets transformed, and that gets sent to the next area of your visual system. So the initial area that receives information is called V1, then the second area is called V2, and so on and so forth. Now, what's interesting is that if you look at the areas that receive that information, at the beginning, like what the V1 area receives, the first area that receives in your brain, they're going to be very simple responses. So it's going to respond to some angles, it's going to respond to some small changes in color, but it's not going to respond, let's say, to faces. So if you look at the activity in your V1 area, it's not going to respond to, say, faces, for example. So if you see someone who is familiar, the brain activity is going to be in a different area of your brain. So what's happening there is that, so let me go back. What's happening is that these basic features are combined and then sent onto the next area of your brain, and that combines again, and so on and so forth. So there is this hierarchical structure where you have small features being combined, creating more complex features, and so on and so forth. And that's what basically we're trying to reproduce with neural networks. How can we take raw features that don't have a lot of meaning in themselves and combine them so that we can make classification or regression more powerful? So just as an anecdote, I guess a study that I like to cite many times is there was this study many years ago. I don't know if you ever watched this TV show called Friends, but there was this study many years ago that showed that many people, because this series was so popular on TV, I'm talking, 20 years ago, for many people, when they saw the image of Jennifer Aniston or the main characters of the series, there will be an area of their brain that will be that would trigger. So there will be like a specific set of neurons match for Jennifer Aniston's face. And what's interesting is that you don't really see that. I mean, the way that happens is that you get this combination of little pieces of let's say the shape of the face, and then that gets combined into the face, the shape of the mouth, and the correspondence between those little features, and then that gets combined into detecting an entire phase. Okay, so if we look at the neuron, this is how that cell looks like. The important thing is that one neuron, this is the body of the neuron, does something we don't know, but then it sends a signal to other neurons through the axon, and those signals are received by the body of another neuron, and then that neuron then receives those signals from many other neurons. So there are many others connected to this neuron, and there is something that happens inside the body, some sort of threshold that is crossed, and then there is an action potential, a trigger that gets triggered. There is a signal that gets triggered because of the information that is receiving. Of course, this is a much more complicated process. I won't go into details, but it's chemistry involved. But we can think of one neuron as some sort of a logistic regression. So you can think of each of the connections. So X here will be the connection from other neurons, be multiplied by whether, how much that neuron affects this neuron, or inhibit the neuron. So if this is positive, that means that it's affecting and maybe giving it the ability to fire. And if it's negative, it's inhibiting the firing of that neuron. So again, there is a lot of chemistry behind this, so I won't get into detail. So the basic idea of a neural network is the neuron, and the basic abstraction from the physical neuron in an artificial neural network is this idea that you have a neuron that receives inputs, and those inputs could be from the environment. So this could be the features of your data set, or it could be input from other neurons. And then there is a small computation that happens here. And that computation that is sent as an output, and that output is received either by the output of the entire neural network, or is something that you send to other neurons. So the way that this will work is that you will have, you arrange these neurons into layers that are not connected among themselves. So this will be layer 1. And each of the neurons in this layer 1 would not be connected to neurons in the same layer. They will be connected to neurons in the next layer. So there is a hierarchy there. And there is a depth of the neural network, where you have these basic connections and being transformed into the next layer, and so on and so forth. Okay, so that's the basic idea, and what's happening inside of the neural network, and how you find these weights, how you find these parameters. Let me go back a little bit. So how you find these weights, you need to learn this from the data, is the entire enterprise of neural networks and artificial intelligence these days. Now, if you compare this, so this architecture with 3 neural networks, is a highly nonlinear hierarchical structure. So this will be, so you kind of think about the output of the neural network as a function of the input, then each of the layers will act as a nonlinear transformation of the input. So you have a nonlinear transformation at the beginning of the first layer, then that gets passed into a second layer that also again gets transformed nonlinearly and produces a nonlinearity of a nonlinearity, and so on and so forth. So it's a very nonlinear function, very complicated. So if you remember what we saw on Tuesday, this interplay between bias and variance, neural networks tend to have a lot of variance. They can fit almost any data set, but you need a lot of data to train them. Okay, so how do we train a neural network? This could be important, or it could not be important. So it's important in the sense of understanding how neural networks are training, what people mean by training neural networks, what they mean by epochs, and if you've heard of these terms, it's basically how long you train the neural network. So it's important to understand what's happening. But it's also not important because these days you have software packages in Python that that do this for you, and you just need to decide on more high-level parameters for those optimizers. But I'm going to give you a gist of how this happens. So the basic idea is that, similar to what we saw on Tuesday, you want to minimize some difference between the training data, the output of your training data, and the output of your neural network. Okay, so you can think of your neural network as just a function of the inputs, and you can define a loss function that will depend on your problem, whether it's a regression problem or a classification problem, and compare that against the real data that you have, the output, right, the label. So a typical example of that would be something like a squared loss. So you just take the difference between your prediction and the actual data and you square that. So that will represent how much mistakes you're making. So you can take this and then you can try to optimize this with calculus. You can try to optimize it by following the gradient. I won't go into too much detail, but the basic idea is that you follow the negative of the gradient. So if we do like a cartoonish view of the parameters, let's say we have one parameter, a neural network, which is one parameter, then that will be the x-axis. And the y-axis will be the loss function, what you are trying to minimize. You're trying to search the point, presumably you're trying to find this point that has the lowest loss, but you have to start from somewhere. So there is no way that you can find that immediately. You have to start from somewhere. And that's what this represents here. This is theta t, is your initial guess. And what you do, you say, okay, I'm going to estimate the slope of this loss function, which could be really complicated, the slope of this function at this point, and I will follow the opposite direction. Okay, the slope here is negative, but you want to move to the right. So you want to do a positive change to the theta. So that's why it's called, you follow the negative of the gradient. And that's what this equation here is representing. Okay, so the gradient is negative, that's here represented. And then you have some learning rates. If this is bigger or smaller, it's how fast or how slow your algorithm converges. And there are multiple issues with that and multiple optimizations that you can do. I would say these days you don't need to worry too much about those issues because there are optimizers that are very sophisticated. And once you find the gradient, your next solution is going to move to the right direction. So this is an example of what will be your next solution. And as you can see, the loss function that you incur, this solution is smaller than the loss function that you have here. That's the basic idea of how you train a neural network. Of course, here, in a real neural network, you have many, many more parameters than just one. You have millions of parameters sometimes. And I think there was a neural network last year that had a trillion parameters. So that doesn't fit in one computer. You need a cluster of computers to train that neural network. Okay, so I'm going to skip this a little bit, but basically there are all these issues that you get stuck in, like not the best solution. So, but people have realized that that doesn't matter too much. Like you can somehow through the optimization process find good solutions, and everything that you see in terms of real applications of neural networks, we don't know if that's the best neural network for the task, but somehow they work. So people start worrying about the problem of not finding the optimal solution to a neural network with the optimal weights. All right, so I'm gonna kind of walk through a simple example, but I would like to ask if you have any questions so far while I enjoy my coffee. No questions? Okay, great. So, and you can post them in the chat or unmute yourself. Okay, so let's think about just one neuron. Okay, so we have one neuron, we have multiple inputs, and there are these special terms that people use in neural networks. So we think of we first define something called the summation, like the linear combination of the weights. So each of these arrows will have a weight associated with them. We call them theta, and which we multiply by the input, the corresponding input, and we just add that linearly. So this is just like a regression. Imagine that this is just a linear regression. And then we have an activation function. So we take this regression and we pass it through an activation function. And usually this activation is a nonlinear function. So typical choices of this is a sigmoid, rectified linear units. All these words basically mean that we will try to find, we'll use an activation that is nonlinear because we want the neural network to be highly nonlinear and complex. So this function here will typically be easy to derive, easy to take the derivative of, and nonlinear. So if we use the sigmoid function, which is this function right here, that becomes simply logistic regression. This is just an example. All right. So now, if we have more than one neuron, well, let me show you what happens with the optimization. But basically, when we try to optimize this neuron with just one neuron, something intuitive happens. But basically, to compute the derivative of the loss function, which is at the very end of the neural network, you have to walk through. You have to use something called the chain rule. You have to walk through the loss function derivative all the way to the weight. Okay, so there is this, you want to take the derivative of the loss function with respect to the weight, but to do that, you do this multiplication. Okay, and what happens is that this idea of chain ruling the optimization allows you to be very efficient in the computation, and we'll see that in the next once we expand into multiple layers. Okay, so imagine now that instead of having just one neuron, we have multiple neurons and multiple layers. So in the 80s, there was this realization that through when you are optimizing, instead of recomputing each of these derivatives from scratch, because of this property of multiplication of derivatives, you can reuse some of the solutions from the forward computation into the backward computations. So that's what's called backpropagation. You backpropagate the derivatives. Okay, and here in the notebooks this is the derivation of this rule, but I'm going to skip this to here. Okay, so imagine that we're trying to compute the derivative of layer L2. So imagine we have, layer 1, 2, 3, and then we have layer L2. So it's just before the output. So it will have this complicated, seemingly complicated structure. And let's say we then want to compute the derivative of the previous layer, okay, L-3. What's interesting is that some of these equations here, so especially, well, this part is exactly the same as this part. Okay, so the derivative of the L-3 layer has a big chunk that is the same as the derivative of the L-2 layer. So you can reuse this entire piece here. Okay, so that's the idea of backpropagation. You take the gradients from the end of the neural network and you backpropagate these pieces into the beginning of the neural network. And you can simplify this further and define the backpropagation algorithm like so. Okay, so backpropagation is simply the application of calculus that was invented, I think, 300 years ago, but they like to put these fancy names as backpropagation, but it's an important realization. Now, the basics of these algorithms are used in all neural networks because they all have, independent of the complexity, they all have this structure where you can reuse parts of the computation in the optimization part. So, okay, any questions so far? Okay. Now, so what I showed you before, this idea of perceptrons, of this idea of having neurons stacked in layers and with not a lot of structure, work well, and it works everywhere, but you need a lot of data, you need a lot of computation, or a lot of parameters. So around 2012, well, before then, but I'm just gonna kind of mention the year in which the kind of deep learning became famous, even though the idea was really introduced a couple of years before. But in 2012, someone introduced a new deep neural network for a problem in image classification, similar to what I showed you at the beginning. Like you have images and you want to classify them into different structure, into different objects. And so at the time, optimizing neural networks was really complicated, but so let's see, 10. Okay, so I have 50 minutes. Okay, so they introduced other kinds of more structured neural networks, not just a simple layer by layer neural network, but they introduced something called a convolutional neural network. They really didn't introduce it that year, but they showed that it can work for this kind of problem. They made it work through the combination of clever computation of huge data sets. And the gist of this kind of neural network is that you can capture spatial structure in the data. And there are many examples of these, and I'm putting links that I encourage you to visit, of demos of how these basic neural networks work for classification images, for classifying images, and for many fun and interesting tasks. When you're dealing with temporal data, you can also have another kind of neural network called recurrent neural network, where the structure is not spatial but is temporal. And the idea is that you have a neural network that calls itself up. So you're always using the same function and reusing it multiple times, so you can kind of keep track of the state of the neural network. And so if you visit this, recurrent neural networks have been used for many things. One of them is generating text, and there is this fun demo where you can generate Wikipedia articles from scratch. And people have been taking neural networks and creating have started to create very sophisticated architectures. And I wanted to do a little activity where we skip all of this. Even for playing video games, if you're a video game fan, you've probably seen how neural networks have play StarCraft and Dota 2, etc. Now, one of the cooler applications of neural networks is this idea of creating images from scratch. And I wanted to show you the website. This person does not exist. So if you go here to this website, the website will, when you visit it, it will generate a face from scratch. And this person does not exist in the sense that it's just a neural network to generate a very realistic face. And people have used these. So recently, this was this application from called DALL-E, or DALL-E, I guess. That's a joke. Now I get the joke. But the basic idea is that you take text, and the neural network takes text and generates an images from that. And I'm just going to say science of science, to study scientists studying scientists, I guess other scientists. So the neural network will take this text and encode it, and then we'll try to generate an image out of that encoding. Up to 2 minutes. Should we stare at the screen for 2 minutes? Let's see. I think it takes less than 2 minutes. They're being conservative. Okay, so I want to do a little demo for you, not of these complicated neural networks, but of a simpler neural network. And I want to do an activity. Okay, so we're going to see first that with a traditional regression, we cannot capture some nonlinear relationship in data, that we're going to kind of do feature engineering. what you will do in your typical statistical analysis, let's say interactions, and then we will see that neural networks can do the feature engineering, the interaction discovery for you. And that's where the power comes from. Okay, so here is an image of scientists studying other scientists. This is what the neural networks think is happening. Although I don't see other scientists studying other scientists, but it's kind of fun to see what happens here. So you can input any text there, and it's just fun to see what happens. Okay, so I'm going to go through the first activity. Okay, so because I want to show you the parameters. So this is I click here, playground.tensorflow.org. Is this demo right here? Okay. So this is a neural network that runs on the browser. Okay. So, and I'm gonna, as the instruction said, we're gonna choose the sort problem. So here, the problem we'll choose, and of course, I don't find where that problem is. Is this? Okay, so this is supposed to be the sort problem. Okay. So we click that. This is the sort problem, although it doesn't say the sort problem. Okay, so but this is the problem. So I want to do, I'm going to select just one layer. Okay, so here you can say how many layers. So I'm going to decrease these one layer, and it doesn't matter how many neurons I choose, I believe. I don't think it matters. Okay, but if I click play, the neural network will run and try to learn from this. Oh, it does matter. Okay, so I'm going to use one neuron then. I'm cheating. Okay, so if as I showed you before, one neuron is just regression. So it's logistic regression. As you can see, it cannot learn the a line basically that would separate these two classes. Okay, it cannot do it because there is no way that a line can split this area with this area. So it needs something else. Okay. So what I will do next, I want you to do feature engineering. So I want you to go here to this demo. And click here, which is one neuron, with only one neuron. What are the features that you need to click so that you classify this perfectly? Okay, so I'm going to type that. What features you need to pick to classify perfectly with only one layer and one neuron? Okay, so let's do breakout rooms, obviously. And you go here. I'm going to recreate this, and I guess let's do 7 basics. Okay, so let's take a couple of minutes to go through here. I think I'll share this with the breakout rooms. And then let's see. I'll share not this, I'll share the entire desktop so you can see the question as well. Okay, so this is sharing desktop 1. So this is the neural network. This is the question. Okay, so I want you to do this. What did you discover?
So using the combination of x1, x2 allowed for both the horizontal and vertical separation. And so that the combination of those in that feature let it classify perfectly.
This one?
Yeah.
Yes. Now, what do we call this in statistics?
Interaction.
Interaction, right? So usually you kind of have to come up with these combinations yourself, right? When you're doing like statistical modeling, you're picking features that you think are going to be predictive. So yeah, that classified perfectly. So, but here I want to show you, and here is the power, in my view. This is the easiest way of seeing the power of neural networks. Okay, so instead of doing feature engineering yourself, which is what you did during your breakout room, you said, okay, I'm going to pick this because that perfectly classifying both. I'm going to give it the raw features. Okay, these are the raw features, and I want the neural network to learn how we should combine those features to discover the feature engineering for me. So I deselected that. I'm going to create 3 hidden layers, and I guess here I'm going to cheat a little bit in the sense I want to. I'm going to create just 1 neuron at the end. Maybe add a little bit more neurons. Okay, just to make sure this is going to work. Okay, so I'm inputting just the raw features, but I created a bunch of hidden layers. Okay, and then 1 neuron in the end because I want to see what happens. You can do it. Okay, maybe I need to add a little more. Okay, maybe another neuron, another layer. Okay, so I need to add, I guess I have 3 hidden layers, but I wanted to show you if I put 1 neuron in the end, it's kind of capturing the feature that it's discovering. Okay, so I'm inputting just the raw features, and then the neural network through the learning process, it discovered that it needs to create a neuron. Okay, and here I'm kind of cheating. I'm kind of forcing it to create 1 neuron that represents the entire problem. And the neuron that created, as you can see from the image, is exactly the interaction. Okay, so the only thing you need for this problem is the interaction for the SOR problem. Okay, and you can see that if you scale this to much more complicated problems, such as the one that I showed before, or any problem that uses the image classification, that's basically what the neural network is doing. You are giving it the raw pixels, no interaction, no major feature engineering, and the neural network will learn a neuron, let's say, that represents faces, a neuron that represents ears, a neuron that represents mouth, eyes, and things like that. And that's the power of them. Are there any questions? Okay, so in the environment, there are a couple of other. There is an example with recurrent neural networks. We didn't get to run with a Python library except for what Lixian showed with Spicy. But here you have a notebook for recurrent neural networks with PyTorch, and PyTorch is one of the libraries for running neural networks. Okay, so I'm gonna stop here, take a 15-minute break, and then we'll continue in 15 minutes with Hans' presentation on convolutional neural networks.